Assignment. So if you go to My Math Lab and Mastering, right, this homework 6, which says just for practice, not graded, just so everybody knows, we're not counting it for a grade. Okay? And it's denying me access to my own homework. Hold on a second. Sorry about that. I'm not sure what's going on. I think the settings for it being open. Just give me 1 second. I'm sorry. Something's going on with my lab and mastering. Sometimes if you leave it open for a little too long. Okay. All right. Let me go back and look at it now. Okay, so for some reason it's not assigned, so let me change that. So I'm sorry about that. I thought I had it assigned. Give me 1 second. Pen 1 available at 12 o'clock. So why is it not open? Okay, try it again. Okay. So does everyone have access to it now? Go ahead and refresh your screen. If you don't, let me know, okay? Okay? All right. Gerard, for some reason, I'm not hearing you. Can someone else speak just so I make sure that you guys can speak to me? Somebody say something besides Gerard. Okay, so let me make sure that you guys are not being muted. Something's going on. Let me do this. I'm going to make you guys all co-hosts, and that way you should be able to. I don't know what's going on with this today. Okay. So can someone try to speak now? Let's. Gerard, go ahead and try. Why is that? It's driving me nuts. It shows you're unmuted. Oh, that is so strange. Okay, try again. Gerard, go ahead and try again. That's weird. I don't know why that is. That's so strange. So do me a favor. I'll check the chat if you have a question, because I don't want to spend all day. Sometimes these things you can go down a rabbit hole. If you have a question, please ask in chat, okay? I'm sorry about that. I don't know what's going on with that. Okay. So we're going to go ahead and start off on the homework. And the first question is talking about the standard deviation for the distribution of sample means, okay? So what you want to understand is that when you're working in these problems with a quantitative variable, there's two different things going on, right? So you have a population of the individual values. And this is what we generally think of when we talk about a population, okay? And if you were to plot everyone in that population, just like we were doing with histograms, right, you'd see some sort of distribution. Okay? But we also have a population of sample means. So if we kept on drawing samples, Xbar. If we kept on drawing samples over and over again and computing the X bars, okay, we would get a normal distribution according to the central limit theorem. Okay? So this is my variable, and this is the average, all right? So if this variable has a mean of mu and a standard deviation of sigma, when we go over to the sample means have the same mean. But the standard deviation is the standard deviation of the variable divided by the square root of n. And this is sometimes called the standard error. So you'll hear this term used. They're talking about the standard deviation of the sampling distribution. Okay? So if we go back to the problem, they give you a lot of different choices. It's going to be sigma divided by the square root of n. Okay? Okay, I'm okay. I'm glad you guys are hearing me. Good. Okay, so this is the first one. And this is a really important point, okay? We have two different things running around here, the variables and the sample means. This is one I want to emphasize because even though it's in the book, I didn't give it an actual name. So this is kind of going back to what we were talking about in the error barometer, okay? So when are things unusual? All right? And what does this mean? What's unusual? Okay? So what you did in the error barometer is you guessed at what pi is. Okay? You made an educated guess or a hypothesis, right? So this was a hypothesis. And then what you did was you actually drew a sample of size n from the population. And you asked the question, how likely, and so like some people, I'll give you an example of one person in class. They guessed that the sample percentage was 75%. And from a sample of 1,200, they got a sample percentage of 48%, right? Now common sense tells us it's very unlikely to get a sample where we have 48% in our sample if it comes from a population where the true population percentage is 75%, okay? So here's what's going on. What we do is we look at sample percentages. So these are the sample percentages we get if the actual population percentage was 75%. Okay? And the central limit theorem, if you go through all the mathematics, the central limit theorem tells us that the standard deviation here is about 1.2%. Okay? So this is about 1.25%. And now we want to know how likely is it we could get 48%. So what we do is we look at the relative standing. We'd look at the percentile of 48%. And we'd find that it's basically zero. Okay, when you put this in the StatCrunch, when you tell StatCrunch, hey, I want to look at a data value of 48%, find out what its percentile is in a normal distribution where the mean is 7.5 and the standard deviation is 1.25, StatCrunch will come back and say it's zero. So what do you conclude? Okay? So here's what the book is saying. When a value is more than 3 standard deviations away, so here's what we're saying. If we make an assumption about a parameter value, and this part's important, so you want to listen carefully. So if we make an assumption or a hypothesis, whatever you want to call it, about the value of a parameter, it could be pi, it could be mu, right? But then we take a sample. So our sample estimate has less than a 5% chance of occurring. chance of occurring if our hypothesis is true. Then we conclude that our hypothesis is wrong. Okay? That's where that problem is going from, is about, okay? So, if you go back to the question, okay, the question here is asking, the blank states that if under a given assumption, that's the hypothesis, the probability of a particular observed event is exceptionally small, such as less than 5%, we conclude that the assumption is probably not correct. And the book gives this a name, okay? It's not particularly widely known, but they're going to call this the rare event rule for inferential statistics. I don't care so much about the name, okay? But the concept is really important, okay? The first one's kind of a laugh, right? The second one has nothing to do with this particular rule. This is just the central limit theorem just gives us the probability distribution. The rule range of thumb, again, it's like this. We don't know. It's just a kind of a name for this particular rule, okay? But that's what it's called. Okay? All right. Weights of golden retrievers are normally distributed. Samples of weights of golden retrievers, each of size n equal to 15, are randomly collected and the sample means are found. Is it correct to conclude that the sample means cannot be treated as being from a normal distribution because the sample size is too small? Okay. So here's what's going on with this. We look at the weights of golden retrievers, and we're told that they come from a normal distribution, okay? And we have a sample size of, what was our sample size again? Of 15, okay? And the question is, can we use the central limit theorem in this problem? Okay. I abbreviate, and this is a common abbreviation, okay? So the central limit theorem requires two things to be true, right? So to use the central limit theorem, the requirements are that, first of all, you need a random sample. And the second, you can have one of two conditions satisfied, okay? Either you have to have a sample size of at least 30, or the variable that you're studying has to have a normal distribution. Okay? Oops. All right? But we have that here. We don't have a sample size greater than 30, but as long as we have one of these, right? So our variable does have a normal distribution. So if our sample is random, and we're given that it has a normal distribution, we can use it. Let's go back and make sure it's random. So it says that the sample's randomly collected, so we can use it. So is it correct to conclude that we can't use the normal distribution? No. Okay. So let's see. We'd be a little careful. No, here it is. There's actually 3 no's. There's usually 2 yeses and 2 no's. They threw me off. No, the original population is normally distributed, so the sample means will be normally distributed, okay? Always make sure that you check the conditions are satisfied. All right, good. Okay. Any questions that we have at this point? about anything? Okay, go ahead and enter in chat if you do, because I don't know what's going on, but the sound is not working in Zoom. Okay. All right, so moving on. Jan's all-you-can-eat diner charges $9.25 per customer to eat at the restaurant. Restaurant management finds its expenses per customer based on how much the customer eats and the expenses of labor. And that expense per customer has a distribution that's skewed to the right with a mean of $8.60 and a standard deviation of $3. Complete parts A and B. Okay. So one of the things that I want to emphasize in this course that's important is learning how to read word problems in statistics. Whenever we read a word problem, and I have to do the same thing myself, okay, we have to kind of get our context. So the first thing that we identify is the parameter. And that's easy to identify, right? Because you're either going to see a mean, the words mean, or the word percentage, okay? Or proportion, or so many out of so many people, right? One of those two, okay? When I go back and I read the problem carefully, okay, it's talking about a mean, and I don't see any percentages here, okay? The reason why this is so important is because a mean is a quantitative variable, right? We can only take averages of quantitative variables. Percentage comes from a categorical variable. These things are like night and day. They're very different, okay? So I'm going to be working with a mean. The second thing I want to do is I want to identify the variable. Okay. And that's easy because it's going to be mean of what? That what is the variable. Okay? We have a question. Oops, I'll come back to that. Sorry. Thank you. I must have just skipped over that. Thanks. I'll come back to question 4. I didn't mean to skip it. Thanks. Okay, so let's go back. I want you to take a minute and figure out if you can figure out what it's the mean of. I want you to take a minute. And while you're doing that, I'm going to play with this a little bit. Okay. So when you read this carefully, right, it's the expense per customer. Okay? Find that it's expense per customer based on blah, 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 has a distribution. So this is my variable, expense per customer, right? And what is the population? It's all the people who eat at Jan's Diner, right? Okay? So this is expense per customer. And my population is going to be all the people who eat at Jan's Diner, right? So now I know what mu is. Mu is equal to the average expense per customer. For all of Jan's customers. Okay? Now we have our bearings, okay? We can kind of go from there. And this is super important to do. I know it's time consuming, but trust me, it'll help. Okay, so now we have to make sense of these numbers, right? So how do we make sense of these numbers? This mean of 860, okay? So now I want to make sense of the numbers. I want to assign numbers to values or labels, okay? The things, the quantities, okay? So we're told that we have a mean of 860. What is this? Is this the population mean or a sample mean? Okay. And how do we know? Good. Excellent. Right. So the mean is the average. Is it the population mean? So how do we know for sure? So Trent said population mean. So sometimes we rule things out. How do we know it's not a sample mean? Let's kind of play the devil's advocate. How do we know it's not a sample mean? Anybody can type. There has to be something indicating that it came from a sample, right? Like Jan took a survey of so many customers, right? We don't see that. So this is mu, okay? The standard deviation, exactly, and so Trent had a really good idea also, because we're talking about the distribution. We're told that this is a distribution. When we're talking about a distribution, okay, we're generally talking about a population. And again, I can go back and rule out sample because I don't see anything indicating it came from a sample. So this is how we put things together, okay? The standard deviation is quoted in the same line, so this is the standard deviation of the population. And we're told that has a value of blah, 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 $3. Okay. All right. Now we have our bearings. Now we can actually do the problem. Believe it or not, it takes more time setting up the problem than it does to do it. But trust me, you'll understand what the heck you're doing, okay? All right. So if the 100 customers on a particular day have the characteristics of a random sample from the customer base. In other words, we're saying, let's treat these 100 people as if they're a random sample from the population. Find the mean and standard deviation of the sampling distribution of the restaurant's sample mean expense per customer. Okay, so now we want to find the mean and the standard deviation of the sample means. Okay? So we want to find, so the idea is this is the population. We took a sample of size 100 that's representative of the population. It's random. It's obviously large enough. It's greater than 30. And I want to know what distribution do these Xbars come from. I can use the central limit theorem because I'm told it's a random sample, right? And I have more than 30 people. So I get the green light on the central limit theorem. And it says, hey, these Xbars, these sample means, should have a normal distribution. The mean is the same as the individuals in the population. And the standard deviation is going to be the standard deviation of the individual values divided by the square root of the sample size. Okay? Notice we haven't computed the sample mean yet, okay? But we're saying that we know what they should look like. They should come from this distribution. And when you square root of 100 is 10, right? Divide by 10, I'm going to get 0.3. Okay? So I want to take a minute and I want to show you something, okay? This is the variable, okay? So the variable's right skewed. And it looks like this. And the mean is going to be pulled out, right? This is Xbar. Okay, and it's going to have a standard deviation of 0.3. Okay. Very different, right? The variable and Xbar have totally different distributions. Okay? Questions on anything? Let me just make sure everyone's good. Okay. So now we can actually do the problem. So the mean is the same as before. It's 8.6. You can put whatever it is in. And if you run into any trouble, just say something. And you got to be careful with formatting. Usually Excel is really great when they're units. My math lab is really good. It'll put the $sign out here, right? And the standard deviation, should I put 3 or 0.3? So you guys tell me. .3. Excellent. Okay? Because I'm talking about the sampling distribution. I'm not talking about the individuals. One of the things I like that this book does really well is it uses the word individual a lot. And that's good because that helps you figure out you're talking about the variable and not the estimator, right? Okay, very good, very good. Bingo. Excellent. Very good. Okay, find the probability that a restaurant makes a profit that day. In other words, we want to know because they're charging $9.20 per customer. So the average, right, better not be more than $9.20, right? So they want to know what is the probability that what they're actually having to pay is less than what the customer's paying, right? So now we got to go to StatCrunch. Make sure there aren't any other questions before we move on. Okay. Okay, we're going to get there. We're going to get there. Okay, excellent. Yeah. Okay, so I'm going to go to StatCrunch now. And I need to go a different way than you guys. But I'll get there in a second. So go ahead to StatCrunch and see if you can do that calculation on your own. And I'll be with you guys in 1 second. Okay, StatCrunch, and here we go. All right. So we're going to go to normal calculator, right? And the first thing StatCrunch wants to know is which normal distribution, right? So in my case, my mean's 86 and my standard deviation is 0.3. Yours will be different, right? And I want to know what is the probability that the average is less than 92. Okay. And it's basically 1. Okay. Oh, I'm sorry. I meant to do, my bad. Sorry. It's 8.6. Sorry. Whenever you get a really large number or a really small number, check your work. Okay. So what kind of clued me in was the fact that I saw 1 and I was like, I know it should be large, but it shouldn't be that large. Okay. And there we can see there's 9.2. So the probability, the average is going to be, the average they're having to pay out is going to be less than what they're actually charging, is going to be 97.77%. So that's good, right? That means that they're turning a profit usually. So thousandths, right? Tenths, hundredths, thousandths is a third decimal place. So there we go. I want to make sure everyone's getting this. So if there is anyone that isn't, let me know. And at least we can share screens. If I can see your screen even without us talking a lot, I can figure out what's wrong. I just want to make sure. Okay. So as Trent pointed out, I blithely skipped over 4. Let me go back and deal with that. Okay. For a population of farm workers in a certain country, so they're already telling you the population, right? Suppose that the weekly distribution, the weekly income has a distribution that's skewed to the right with the mean of mu equals 450, standard deviation of sigma equals 170. A researcher unaware of these values plans to randomly sample 100 farm workers and use the sample mean weekly income Xbar to estimate mu. Okay, so again, let's figure out things. Our parameters mu, right? Average of what? Average of weekly income. Average of weekly income for whom? Population of farm workers. See, now you can make sense of this number. Don't just look at it as, oh, mu is equal to 450. Okay, this is saying that the average weekly income of all the farm workers is $450. Now we can make sense of that number, right? And the standard deviation of the weekly income for all the population of farm workers is 170. Okay? All right. What is the standard deviation of X bar? Okay, that's just going to be 170, right? Is that correct? The standard deviation of X bar, is that going to be 170? Anybody? Nope. Because I'm not looking at X, right? I'm looking at the sample mean. I'm not looking at the variable. So I'm going to take, so I know my formula here, right? My formula tells me that, and sometimes people use this notation, and I personally like this a lot. They use standard deviation of X bar. They use standard deviation of X for the variable and standard deviation of X bar for the standard deviation of the sample mean. Okay? And personally, I like this notation. I'm not going to use this for you guys, but this is a really good notation to use because now I understand what standard deviation I'm looking at, right? This tells me. Okay, so the central limit theorem, right? My sample is large and it's random. Okay, it's large because 100 is greater than or equal to 30. And it's random because I'm told so. Okay? And so I get the green light on the central limit theorem, right? And so go ahead and write out what your version of the central limit theorem is. Mine, for this problem, is going to be that X bar has a mean that's the same as the mean of the population, which is 470, and the standard deviation is 1.7. Check my numbers here really quick. 450, sorry. My bad. Okay? So go ahead and write out what yours is. In fact, I'd like everyone to write out using this notation. Go ahead and write out this. I want everybody to do this. Then put the value for your mean in and put the value for your standard deviation. I want everybody to do this. And the reason why I want everyone to type that in chat, I'd like you to do that right now, is because I want to see that you understand the notation, that you feel comfortable, and you understand what to put in where, okay? Because I'm going to use this notation a lot. So Gerard, go ahead and type in what it is for your problem. And then David, and then Kayla. Are people typing or am I not getting chat now? So frustrating. Okay. All right. X bar. That looks good. Actually, I think I screwed up, didn't I? I screwed up. This should be 17. Sorry. Thanks. It's 170 divided by 10. Sorry. Very good. Okay. David, Kayla, what do you guys have? Francisco, I don't want to leave anyone out. Trent? Looks good, Francisco. Okay, good. All right, thanks. Good, good. Okay, very good. Good. We got everybody, Trent? I'm doing this wrong. Okay, so tell me what, so first of all, type in what mu is. Type mu is equal to from your problem. And then standard deviation is equal to, and this is for the variable. Okay. See, what we're saying here for the sample mean is we're saying that the mean of the sample mean is the same as the mean of the variable, right? That's this first value right here. And to find the standard deviation, you're going to take the standard deviation of the variable and divide it by the square root of the sample size, okay? Okay, so your sample size is your sample size 100? Okay, so go ahead. So your standard deviation, what will your standard deviation be? For X bar, your standard deviation of X bar is going to be the standard deviation of the variable divided by the square root of the sample size, right? So this will be 168 divided by the square root of 144. Okay? Exactly. Bingo. You got it. Square root of 144 happens to be 12, and it goes in evenly. It goes in 14 times. Excellent. Very good. All right. Good. We're all on the same page. Excellent. Okay. Let's go back to our regularly scheduled program. For my case, it is 17. Go ahead and type in yours. Okay. Good thing I saw Gerard's answer, because I would have typed in 1.7 mistakenly, and then I would have had to go back and figure out what I did. Explain why it's almost certain that the sample mean will fall within $51 of 450. Okay, so let's kind of look at what's going on, and I want you to make the same sort of sketch in your problem, okay? So in my problem, my X bar was 450. Okay, that was the mean of X bar. Okay? And my standard deviation was 17. Okay? And so we're going to draw a normal distribution, and I'm going to step out in units of standard deviation, which is 17, right? So this is 467, 484, right? 501, then I'm going to subtract off, right? So this is 433, 416, and 416 and 399. Okay? I want you to do the same thing. Okay? Take that mean that you just told me you got and your standard deviation and sketch this out. Okay, so what was your, so let's see, let's go back up and see. So Francisco, what was your sample size? Go ahead and type n is equal to whatever your sample size was. So here's what you want to do. You want to take the standard deviation in your problem, right? Whatever it is, and divide it by the square root of your sample size. Okay, so your standard deviation is 176, and your sample size is what? So you've taken the square root of 121, okay? So this is the standard deviation of the variable. This whole thing is the standard deviation of X bar. So when you compute that out, what do you get? You should get 16, right? Yeah. Right, so our values are going to differ. That's right. Yeah. Okay, good, yeah. So that'll be 176 divided by 11, and that turns out to be 16, divides it evenly. All right, good. These are good things. Stop me when you're missing stuff like this, because I want to make sure, okay? Okay, so it's asking, why are they guaranteed to be within $51? Well, if I look at this, $51 is 3 standard deviations, right? For my problem, the standard deviation of Xbar was 17. So if I take 3 standard deviations, okay, 3 times 17 is 51. Okay? So this rare event for inferential statistics, this rule that they have, okay, we know from the empirical rule that 99.7% of the values, if we have a normal distribution, lies within 3 standard deviations, right? So it's very unlikely to get a value outside of that. Okay? And so A looks good. The empirical rule says nothing about 51 units. Okay, that's like baloney. That doesn't make any sense. The empirical rule is measuring distances in units of standard deviation. So B is just a nonsense answer. You have to be a little careful. 95% fall within 2 standard deviations. So you have to realize that all or nearly all is really saying 99.7%. You can also note that $51 is not 2 standard deviations, it's 3. Okay? So hopefully that will help you kind of puzzle through it. All right? Okay. The sampling distribution of Xbar provides the probability that Xbar falls within a certain distance of mu, regardless of the value of mu. Calculate the probability that Xbar falls within $20 of mu. Okay, so again, this is a stat crunch question, right? They want to know what is the probability that you're going to be $20 from the average, right? So I'm going to use between here. And go ahead and put in whatever mu was. And now you're going to put in the standard deviation for Xbar. Okay. Can I go back and make sure I use the right values myself? Just check really quick. I had 17, yeah, 450 and 17, okay. Okay. And I want to know the probability that the sample means within $20 of the actual mean. So 20 below would be 430, right? And 20 above would be 470. Now, you should know already without doing any calculations, it's going to be pretty likely, right? These values are roughly one, in my case, they're roughly 1 standard deviation. Standard deviation is 17. I'm looking at 20, okay, above or below. So it's going to be around 68%, a little bit higher. Okay? And I'm going to get an answer that looks like that. So my answer is going to be 0.7606. And I'll go ahead and paste that in. And just watch the rounding. Okay? Okay. Okie doke. Any questions before we go on? Anything that's not working out? Now's the time for truth. Okay? All right, good. Okay, so we can move on then. And by the way, you can practice similar problems, right? You can use this, you can do this over and over again, okay? Annual incomes are known to have a distribution that's skewed to the right, which is something we know instead of being normally distributed. Assume that we collect a large random sample of annual incomes. Can the distribution of incomes in that sample be approximated by a normal distribution because the sample is large. Okay, so what are the conditions that are satisfied here? I want you guys to tell me. There are two conditions here. Which conditions are being satisfied? Is it random? Do I have a random sample? Yeah. I'm told, right? Comes right out and tells me. So if I have a random sample, all I need to look for is that my variable has a normal distribution, which it doesn't, or my sample is at least 30, okay? Which it is. So I can use the normal distribution, okay, for the sample means. So the only one here is yes. So should I click yes? Am I thinking about this problem correctly? I mean, I'm saying I can use the sample means, right? I can use central limit theorem. Is that what the question is asking me? Anybody? So let me ask you a question. Is the distribution for Xbar normal? Yes or no? Anybody? Okay, if you say no, then you have to tell me why. I'm talking about Xbar, the sample mean. So if you're going to say no, you have to tell me which condition didn't I satisfy? So you guys are on the right track. Notice Xbar is normal. And so this is where you have to really pay careful attention. Can the distribution of incomes, okay? So let me just sketch this out, just to make sure everyone's on the same page here, okay? This is the distribution of incomes, right skewed. Okay? The distribution of average incomes is going to be normal. Okay? But they didn't ask about the average income. They asked for the distribution of incomes. Right? So they're trying to trick you. They want you to automatically say, oh yeah, it's random and greater than 30, therefore the distribution of incomes is going to be normal. That will never change. The distribution of the incomes is the population variable. That's never going to change. That will never be normal. And you're told that. So the answer is no. Again, it has nothing to do with the sample sizes, right? That's the estimator, okay? The population of incomes is not normally distributed, so the sample means will not be normally distributed. No, again, the sample means will be normally distributed. So the sample means will be normally distributed, but samples of income, in other words, if I take a sample and I look at the distribution of the incomes, they'll be skewed to the right. This is a good problem to think about. If anyone wants to talk about this a little bit more, go ahead and type in the chat. Okay. This is a good problem to make sure that you understand carefully, okay? And you understand really well. Okay. All right. So the overhead reach distances of adult females is normally distributed with a mean of 202.5 centimeters and a standard deviation of 8.3. Okay, so first of all, I'll get my bearings. What is my parameter? Mean of what? mean of overreach distances of whom adult females. So now I can make sense of all this. So I'm going to go ahead and write this out, okay? Mu and sigma. And I'm going to split the screen so I can see both things at the same time. I'm going to try. Okay. All right. Okay, so the mean here is 202.5, and the standard deviation is 8.3. And this is of the population. This is my variable, right? Okay. What is the probability that an individual distance is greater than 215? Again, individual, so I'm working from this population, right? So I can go right into StatCrunch and do that calculation, and I'd like you to do that along with me. Okay. So we'll go ahead and put in the given value of the mean, whatever yours is. Your standard deviation is 8.3. Yours will be different, of course. And I want to know the probability that an individual distance is greater than. So I'm going to have to go back to standard. And the tricky part is I need to change that to greater to, right? And that's 215. Cool thing about StatCrunch is it gives you that colored portion, right? So the individuals that are greater than 215 live in this interval above 215. So the probability I can be above 215 is the area under the curve for those individuals. And this is my answer. 0.1, 2, 3, 4. And that'll be my answer. Okay? All right. So now they want to know about averages, right? Before we go further, let's kind of make sure. Mine didn't accept it. It's not letting out two. So let's see. You went to normal calculator, okay, and type in the values. Yeah. So again, you got to be careful with the decimal places, right? So when I copy these things over myself, here's how I do it. I go 1, 2, 3, 4, and then I look and see the next decimal place over, right? So if it's 5 or greater, I'm going to round up. Okay. If it's not, I'm going to keep it the way it is. So in my case, it was 3, so I'm going to leave it at 0. Okay. So why don't we share screens here to see what's going on, Francisco? Let's see. Hold on. I'll make you, actually you are co-host, so go ahead and share your screen. Let's just see really quick what's happening here. If you go to the bottom here, you should be able to share. Oh, good, Trent. All right. So Francisco, okay, good. So what happened, if you don't mind me asking? Did you just type it in, or did you round it wrong, or? Yeah, it's easy to do. That's easy to do. Yeah. Okay, good. I'm glad we're all good now. Okay. So now it talks about the probability that the mean of 20 randomly selected distances is greater than 20.7. I can't use the same values, right? Because now I have to be careful, right? I have to ask, can I use the central limit theorem? I can, because the variable itself is normally distributed, right? And we're told that we have randomly selected people, so we're okay. We get the green light. So the central limit theorem says, okay, for the means, when n is equal to 20, right, they're going to have the same population mean. So your value will stay the same. Mine happens to be 202.5. But this is going to be 8.3 divided by the square root of whatever the sample size is, right? Mine happens to be 20. So I'm going to go ahead and compute mine. And you can go ahead and do yours. Now, one thing I'm going to warn you about, when you plug the standard deviation into StatCrunch, go out to 6 decimal places, okay? Because it can be really kind of sensitive to round off error, okay? Oh, come on. Okay. So I'm going to use 1 point, and I'm going to literally just copy and paste this, okay? 855,936, and put this right into StatCrunch. Okay? Oops, wrong place. No, that was the right place, sorry. And I want the probability, if I go back to the actual problem, right? I want the probability that I get a distance greater than 200.7. And there we are. Okay? So all you're going to change in this problem is the standard deviation. And the reason why is you're not looking at the individual, you're looking at the mean. And we know the standard deviation for the mean is going to be different. Yeah, and you can do this a number of different ways. The easiest way to do it is just, if you use it in your calculator, just put in out to so many decimal places. Just put in at least 6 decimal places, and you don't have to worry about the rounding. If you go that far off, that far out, you'll be fine. Okay. Right, exactly. That's what the central limit theorem is telling you. The central limit theorem is telling you, when you look at the variable, okay, so the variable can be skewed like this. Okay. The variable can be skewed. For some reason, that pen's gone out. Hold on. Okay. So the variable itself can be skewed, and the mean will be way out here. But what the central limit theorem tells us is that the sample means have the same center. Okay. So they're both centered at mu. Okay? It's just the standard deviations that are changing, right? The standard deviation here, so the mean is mu, and just the standard deviation is changing. Yeah, whatever it is, right? It's a standard deviation of whatever you had divided by your sample size. Whatever that is. So go ahead and put that in and see if you can get it to work. Did it work okay this time? Let's just make sure. And if not, you can always share screen, Trent. You guys all should be able to share screen, I think. Yes, screen share, sorry. Okay? Okay. So okay means that you got the right answer, Trent? I just want to make sure. Okay, so can you share your screen? Go ahead to the bottom, and you can do this. No, it's not working for me. Yes. Okay, which is it? Is it working? Did you get the right answer? Let me just make sure. Well, I'm sorry, Gerard. I didn't mean to. I meant to respond to Trent. Okay, can you please screen share? Because I can't see without seeing your work what's going on. Hold on. Let me go back. Maybe I didn't set you so you could do screen share. I thought I did. Yeah, you're down at the bottom of the list. Hold on. Yep, I didn't make you a co-host. Sorry. There you go. Okay, now we can screen share. Okay. All right. So let's see your problem. So your standard deviation is 8.3. Okay. And so the standard deviation for X bar is going to be 8.3 divided by 25, the square root of 25, right? Because now we're talking about the means. So their standard deviation is the standard deviation of your variable divided by the square root of your sample size, right? So what did you get when you did that calculation? Let's see. Let's go ahead and work it out. I'll work it out on my calculator. Make sure we're getting the same answer here, okay? So it's going to be 8.3 divided by 5. So you'll get 1.66. Okay? All right? 25 square root. Bingo. Okay, so now we want to go to StatCrunch, right? So let's go ahead and pull up StatCrunch. And show us what you're going to do in StatCrunch now. Okay. Yeah, that's going to totally change, right? Okay. And we want the probability that we're greater. Bingo, bango. That looks good. All right. And so you just got to be careful what it's asking for. If it's talking about the mean, you're going to be using the sampling distribution. Excellente. All right, very good. Okay. So, back to our regularly scheduled program, right? I didn't put in my probability. Let me do that really quick. 1, 2, 3, 4. And there we are. All right. Why can the normal distribution be used even though the sample size does not exceed 30? It's because we had a normal distribution, right? And again, the normal distribution refers to the original population, okay? The actual variable, not the mean. All right, very good. Let's see, we got some questions here. Oh, why is the chat thing not showing up? Come on. Oh, hold on. For some reason, my chat window's buried. I don't know why. That's weird. There it is. Okay. All right. Very good. Very good. Yeah, I don't know, Gerard. You're also doing private messaging. I'm not sure why. I might have said something wonky. Let me just see really quick. Okay, I don't see anything weird. You look okay, but I'm not sure. Okay. All right, good deal. So let's go ahead and go forward if there aren't any other questions on that. This is a good problem. These next two problems are really good. An airline carries 200 passengers and has doors with a height of 72 inches. Heights of men are normally distributed with a mean of 69 and a standard deviation of 2.8. Again, let's sit down and kind of figure out what's going on, okay? So what is my parameter? My parameter is a mean. Mean of what? Mean of heights. Mean of heights from who? Mean of heights of all men. Okay? So I'm looking at a mean. My variable is heights. And my population is all men. Okay. So I'm told that for this population, which is, we know is generally going to be normally distributed, heights are, right? This is the height. We're told that the mean is 69, and the standard deviation is about 2.8 inches. Okay? So we know here that the mean of the height is 69 inches, and the standard deviation of heights is 2.8. Okay? Now we have our bearings, all right? If a male passenger is randomly selected, find the probability he can fit through the door without bending. So what do we want? We want the probability that an individual is less than 72 inches, right? So I'm going to go into StatCrunch and enter these values, and then ask StatCrunch to tell me the probability that X is less than or equal to 72. Okay? So let's go ahead and do that. You can do that for your values, right? So the average here is 69, and the standard deviation is 2.8. And I want to know what is the probability that a randomly chosen person will be less than 72 inches. Okay. And there we are. So this is going to be 0.8580. Of course, yours will be a little different. Okay. Check our answer. Crowd goes wild. Okay. I'm going to wait for a minute, make sure that everyone has this before we go on. It's going to take a minute. Okay, so now for the $9 million question and the year's supply of turtle wax. When I do the next problem, okay, if half of the 200 passengers are men, to find the probability that the mean height of the 100 men is less than 72 inches. What is the one thing I'm going to change in this StatCrunch calculation? Anybody? What am I going to change? One number and one number only. What is it going to be? Anybody? Standard deviation. Bingo. So in my case, I'm going to take 2.8 and divide it by the square root of 100, right? That's the number of men I had. And that will give me my answer. So you're absolutely right. So you're going to take whatever the standard deviation is. Mine was 2.8. So we're going to say that the standard deviation of the average height is going to be equal to the standard deviation of the heights of men divided by the square root of the number of men, which is 100. Okay. And again, notice it's very different, right? It's basically 1. Why? Because 69 and 72 are much more than 3 standard deviations away, right? This is about 9 standard deviations away. So the probability I'm going to be less than it is basically 1. Okay. Very different, right? Okay. So before we move on, go ahead and check your answer. Make sure you're getting that right. In this last part, they want to know which is more relevant. Okay. The average heights or the individual heights. Okay. Well, we're more interested in the individuals. We don't care about the average. Okay, notice it's very easy for the average to be less than 72, okay? So, but it's the individual that has to worry about ducking. It's not the average, right? So the probability from part A is more relevant, okay? So it shows that the proportion of male passengers that will not need to bend. So this is where you have to kind of think about what's being asked in the problem, right? It isn't the average of those 100 men that have to worry about bending. It's each individual person, right? Why are women ignored? Well, women are generally smaller than men, right? So if it accommodates men, it's going to accommodate a greater proportion of women. By the way, I'm going to make an observation here, and this is important. This has nothing to do with the problem, but it's worthwhile you knowing. Things are generally designed for men, okay? And in this case, it's not a big deal because women are generally shorter, right? So if men can generally go through, women, a higher proportion of women are going to be able to go through. However, sometimes it's really important. For example, when they make crash test dummies, okay, for automobile safety, they use a crash test dummy that weighs the same as a man. Guess what? Women weigh less. Guess what? There's catastrophic consequences. More women, 77% more women die in a head-on collision than men. And the reason why is the safety designs are engineered for men, not women, and it does make a difference. So that's an important thing to understand. Okay. We have a few minutes left. I'm going to talk about setting this problem up. This is a good problem to do. I want you to do this, okay? So it says, before every flight, the pilot must verify the total weight of the load is less than the maximum allowable load for the aircraft. The aircraft can carry 42 passengers, and the flight has enough fuel and baggage that allows for a total passenger load of 6,888 pounds. The pilot sees the plane is full and all the passengers are men. Okay. The aircraft will be overloaded if the mean weight of the passengers is greater than 164. Okay. In other words, they're taking the total weight allowed and dividing by the maximum number of passengers. Should the pilot take any action to correct for an overloaded aircraft? Assume the weights of men are normally distributed with a mean of 104 pounds and a standard deviation of 39.2. Okay, so what do we know? We know that for men, the average weight is 180.4 and the standard deviation is 39.2. If we look at the average weights of 42 men, the average is going to be the same, right? The central limit theorem tells us it's still 180.4. But that standard deviation is going to be 39.2 divided by the square root of 42. Okay? And go ahead and put your numbers in your calculator. By the way, if you use StatCrunch is really good because it will automatically round off everything. Okay? I don't open up StatCrunch because I have too many windows open as it is, okay? That's my standard deviation. So this is what the average, the population of average weights for men look like, right? Centered at 180.4, and my standard deviation is roughly about 6. And I want to know in this problem, what is the probability that the average weight's going to be more than 164 pounds? Well, it's very likely, right? I mean, this is actually below the mean, okay? So I'm going to go ahead and use these two numbers, 180 and this number here, and put this in the StatCrunch. And I know we're hopping around a lot from window to window, but So this is 180.4. And my standard deviation, you can put in whatever yours is, 6.04869. And I want to know what is the probability that the average is going to be above 164. Very likely, right? Should the pilot do anything? Heck yeah. Okay. There's a 99.7% chance that the plane's going to be overloaded. Okay. And by the way, talking about safety, okay, this is how people get in trouble with the law. This is how people get sued for gross negligence, okay? Companies that should have checked this sort of thing and they didn't. Because in a court of law, the prosecuting attorney would say, well, you knew or you should have known there was a 99.7% chance your plane was overloaded. Why didn't you do something? And that person would be in serious trouble. Okay, so this is probably the last problem we're going to have a chance to do today. If there's any questions, I'll stay behind. Okay, if not, you guys are free to leave of your own recognizance, and I will see you later. Go back. I didn't see D. Sorry, let me go back. D for which problem? Let's see. D for the problem before that. Hold on. All we were saying for D was that women are shorter than men. So if the men are okay, a larger portion of women will be less than 72 inches. That's all we were saying there. Okay. Okay. All right. Excellent. Thanks, Gerard. Okay. Question 6. You sure can. I have a special today on questions. Let's see. 7, 6. All right. So the sample means are normally distributed, and the reason why is we took a large sample and it was random. Okay. So when we're checking to see if the sample means have a normal distribution, okay. So the sample means have a normal distribution if it's random, right? If our sample is random, and either the variable has a normal distribution, which it doesn't, because the variable is income, it's right skewed, or we have a large enough sample, right? And so we're told in the problem that the sample is random because it comes right out and says, assume we collect a large random sample, so that's okay. It's not from a normal distribution, but we have a large enough sample size. Okay. All right. Oh, 7. No problem. Let's go back to 7. Yeah. So we calculated A using the variable, B using the sampling distribution because they wanted the mean, and they told us the sample size. And then they asked, can we still use the normal distribution for Xbar because we don't have a large sample size? So let me know which of those parts. So questions that we have on any of those, on any of that? Okay, excellent. All right. Thanks, Francisco. I appreciate it. All right, good deal. Okay. If we have any other questions, feel free to ask. I can hang around. I'm not giving the homework problems because I want you guys to be able to do these first, okay? 8B. Let's look at 8B. Okay, so 8B. Let's see. Okay. So if half of the passengers are men, so your sample size is 100, right? And so you're going to take the same mean and the same standard deviation, but you're going to divide your standard deviation by the sample size, right? And here you have 100 men. That's your sample size. Or in your case, it'll be a different value, right? Yeah, interesting. Yeah, I'm not surprised. Those sorts of things actually happen. They're not just textbook problems. They actually do happen. Yeah. So Trent, let me know what and again, if you want to share screens, I can see what you're doing. Okay, excellent. Okay, let's see how let's see how it works now. How's it? So you use your sample size. So you're given as 125 men. There's 250 passengers, but half of them are men. So it's 125. And in the problem statement, it says the mean height of the 125 men, right? Because half the passengers are women and half are men, right? Okay? Yeah, so use the 125. And of course, the square root of 125, you have to figure it out, right? It's not a nice, easy, not a nice, even number. Okay, so let's see what we get. Let's make sure we get the right answer. No, 2.8 divided by the square root of 125, that will be very much smaller, right? So your standard deviation here is 2, where did I get that? 2.8. So 2.8 divided by the square root of 1. Oh, I see what you're saying. Right, the square root of 125. Gotcha. Excellent. That's right. So you're going to get standard deviation like 0.25, yeah. Okay, let's see. I got the same thing you got. Yes, I got this. So again, remember what you're doing here. Let me just type this in really quick, right? So you're saying 2.8 divided by the square root of 125, which is equal to 2.8 divided by 11.8 whatever. Oh, for some reason I'm messaging. Hold on a second. Hold on one second. Okay. Yeah, then never mind. I'm going to type it in right here. It's a pain in the butt, this thing. Hold on a second. Yeah, so let me go back to mine, and I'll show you what I'm typing in here. So all I'm typing in is this. I'm taking my standard deviation and dividing it by the square root of the sample size. That's all we're going to do here, right? So it looks like this. Okay? And you're just going to compute out that number. And when you do that, you're going to get a roughly about 0.25. Okay? Does that make sense? Are you seeing that now? Can I go back? So you're going to get roughly about 0.25. That's going to be your standard deviation, right? So this goes back to the formula, right? You have to remember the formula, Trent. The formula says the following. It says the standard deviation for the averages is the standard deviation of your variable divided by the square root of your sample size, okay? All right? So your variable is height, so your standard deviation of the height is going to be 2.8, and your sample size is 125. Okay? That's what we're doing. Okay? So let's go back to sharing screens. I'd like you to do that calculation. You'll get about 0.25, and let's see how it works out. Okay. See, the 11.8, that was the square root of the sample size. Okay?